Yeah, so welcome to our session today. Yeah, I was asked to give overview to the current technical development of InChI. Some people who were in Cambridge may know major parts of that. Obviously, within 3 months and a little bit of vacation in between, not so many things happen, but a few minor details are quite interesting. And of course, you will see that some of the chapters have changed because from work we want to do, we come over to work we did. And worked once. Yeah. Okay. Interesting. I'm not used to this very enhanced technique. I always see my PC in front. All of you may have seen this graphics that Jonathan once developed with all the different keys and the InChIs and whatever is all around in the environment. And more or less, we are handling most of them during this talk already, some part, but during our meeting, we'll come we will go through this graphics on a wider scale. Anyway, that's what I want to talk about. A little bit about the InChI release status, what we're going to run in terms of programming next round. I would like to come back to the discussion of how do we call our InChI versions, because that will become interesting for the next half a year or so. And then a little bit an overview to those InChI working groups that are currently being active to be implemented or have been implemented. Yeah, for the others, that will follow up later on during this meeting. So let's start with the release status. All of you have seen this one already, but it has changed a little bit. Obviously, 1.07.0 is out, and it's officially out. UPAC, CPT, CVDS, and all the other areas said yes, and with that one, it's official. And with that one, it's the official InChI now. It doesn't sound that exciting, but if you did the work, and thanks to all of you that are in or just on connected digitally, it was quite a bit. And because we had to rebuild the entire infrastructure, for example, for testing, whatever is necessary to come out with it. So what has been done, more than 3,000 issues have been cleaned up. George will talk about that a little bit later, some more details coming up. Polymers continue to be in beta status, something to be discussed later. And 6 tautomer transformation as a test for Mark Nicklaus' paper have been implemented and now can be tested. We need the feedback to see how it works, and then with positive feedback, we have to see how we're going to continue with the implementation later on. Where do we stay right now? You see under development, we've got requirements, sometimes nearly ready, especially for the molecular inorganics and for the molecular inorganics and organometallics, which is a big round because we had a meeting over here in Aachen 2 months ago with a bunch of discussions, and I think we will continue tomorrow morning with the next round, because the further you go into that one, the more things you'll find, more interesting things you find, and there will be a lot of fun to program them at the end, but we need some type of vision how to do that. Stereochemistry, Andre is over here saying a few things about it. Tautomers, as said, we've got those 6 examples. S groups and S group data are part of the polymer story. We need a little bit more of that implementation, partly internally as well, for example, for the isotopologues, because they rely on S group data like some other reaction InChI stuff as well. And of course, we have got the Makush InChIs, represented by Jonathan, who is still on the train ride, and the large molecule represented by Evan, who is online. On the other hand, we've got the applied InChI framework, basically reaction InChI, mixture InChI, non-InChI. Those are the most important ones. And as a new part, the web demo, which is formally, well, actually, it's not true anymore, because the InChI 1.0 release has been released, and with that one, the following up, the web demo should be released as well, officially. Okay, but nevertheless, the reaction InChI 1.0 is out. Reaction InChI 1.1 is ready to come out now as well, because that is relying on 1.07. It means that I have to do the testing now, and some more words about that a little bit later. During that meeting over here in Aachen, we are going to have a discussion about mixture InChIs and nano InChIs and reaction InChIs, because we hope that we can share some work and some formats. And we have to make sure that you can run a reaction over mixture InChIs that may come up to a nano InChI, whatever. Yeah, they have to be interchangeable. But that means as well that we need some rules, some naming rules, for example, to make sure that we still have unique nomenclatures in there and not a mixer of the same same letter character for different things. Yeah, that's where we are right now. I think there's a lot of work. Slowly you see changes in those slides. The other one you see now as well is 107.0 has been approved on the 16th of July, so last week. And the other ones had to be moved slightly to the back again. Partly as well because the approval process takes much more time than I thought about, for example. Yeah, we are already 2 or 3 months in circles around that one, while we are still fixing some Google Fuzz issues, but in terms of the functionality that is already provided for a longer time. Yeah, and you see that those are the major changes in that diagram. This is the current status. Okay, coming back to the current release now, which is out. We already mentioned the tautomere transformations. We have got 2 fixes. So basically, it's really just to regain what was there before and knowing about the code. That was the most important point for us, because now we can really work with the code, unlike before, if it was a black box. We left the black box and just massage very simple errors, those 2 that are mentioned over there, and a lot of Google Fuzz issues, more than 3,000 is mentioned already. And George is willing to tell you all about it into details, whatever you'd like to hear. Yeah, so he's going to talk about buffer overflows, memory leaks, segmentation faults, and a very long list of that kind of special parts. To make his life and our life easier, he has started to take some parts of the Google Fuzz environment over to his development machine, so that we learn faster than just waiting for Google and the next report. And what we have seen now for the last 3 months, the number of reports coming back from Google is coming down, and I think per release we've got 2 or 3 new ones, and most likely 3 or 4 fixed ones. So the balance at the end is towards going down. We've got already 1 major bug report being reported by Gerd Blanke of OpenEye nowadays. And Gerd, that will come up in a sub-release called 1.07.1. And you see now we're becoming a little bit agile over here. Yeah, so we do not wait until the next big release. We would like to have those parts implemented faster, so that we can continue to work with Google as well and do not lose the track over there. Just to mention, for between 106 and 107, there is 1 big change in terms of license. Now we are just on a clear MIT license. And that makes life easier, more open. Stuff can be reused by whomever. But we must have in mind that the older versions are still on the old license, and we may think about the InChI Trust if we have to change it or not. But the 107.0 release is the official one now, so most likely not. We did a lot of work about compiler version. I learned a lot. To be honest, I hate compilers. Sorry, no, George. They should just work. But it was really quite impressive to see that sometimes even the compiler version as such, and some of the options as we found out at the end, may lead to the point that 5 structures, for example, all of them have got one system of 1 nitrogen, And I think 4 tritium atoms and a iodine atom all around. It's our party crasher, by the way, that compound, because that gave the error messages but only in 12, 13, and 14. And at the end, George found out we have to change the compilation options to make that work. The Microsoft compiler were fine, and of course, just released. The next question came up, Mac version. You see the typical issues for Europeans because Macs are not that much used in chem informatics over here. So that's always the thing it's secondary for us. But if you come up to English-speaking areas, it's primary. And on the other hand, Mac is not that nice to program, to be honest. Do you like it, George? No. Okay. Oh, fine. Good to hear. One of the problems they change the versions pretty frequently. And that leads to a higher level of maintenance. The simple way we try to offer is that we have a makefile that compiles with Mac. I will come back to that in the reaction InChI context, because there we got some help from ChemExon to do that. If we are able to compile binary versions, we have to discuss, because out of the maintenance effect. So testing, more to report it by George later on, testing as well by Jan. What type of tests has been done? After all the discussions we had, we primarily focused to PubChem, but we went away from the nice and clean compound level to the nasty and raw data level called substance tests. Yeah, there you get everything somebody puts in. And my feeling is that is a realistic life of InChI, because in most of the cases, there is not a structure normalization. Or if there is a normalization, it's not the one that has been used, for example, for PubChem. So at the end, we primarily focus to the compound 3D part to make sure that the 3D works, and to the substances, and to see substance level has got 306 million about chemical structures to test, with 280 or 90 million that are real structures and no structures. The results are quite impressive, but you must have in mind the version hasn't changed. So we could do a simple regression test between 106 and 107. So the results that have been achieved with 106 have to be reproduced by 107. And that has been done pretty well. To be honest, we only have a very few outliers. The outliers are primarily in an area where we have the H-atom tautomeric systems over there spread around, where obviously some of the iterations are stopped at a certain point so that you do not reproduce the results. And that is really coming out in the invariance test, where we got 2,131 of those structures that do differ in 6 in the 3D compound part. And Paul, in German, Tyson, don't know how to talk in English, working for Evan, he found 3 compounds in terms of stereochemistry that I would have to look into after this meeting, but most likely they are covered already over here. That's what I assume. Yeah, for the invariance tests, we've discussed multiple ways. There is a tool within InChI, and there's an RDKit tool. We started with the RDKit tool, but it may not be the last answer. Still working, finding out the pros and cons of each of those tools. Besides that one, we are going to introduce so-called unit tests on GitHub. Unit tests are just run just straight after the compilation, so that you know that your compilation has not harmed anything. Meaning the unit test should represent your, in our case, chemical space we have to address. Yeah, so a good variety of chemical structures plus our special cases we have to follow up should be in there. Besides that one, of course, InChI parameters will be an ongoing story anyway, because there will be new ones. And now what type of test to run when? If we have got a new sub-release, so .0, .1, .2, .3 now, We are just running the, we just go to regression tests because they already give a very good overview, you know, if there have been any dangerous changes done to the code. If we come up to a major release, we do invariance tests. Yeah, and having in mind that invariance test takes about 5 days. Yeah, roughly about 5 days, and therefore that is a little bit limited to be used. Beside that one, we've got the Docker station that can be found in the test area, can be compiled from there. With the Docker station, you can download everything onto your own local machine and do the test within your environment, meaning your structures do not leave your environment as well, and you can just report the results. Yeah, so for companies, for example, this is a very nice way to fulfill their protection interests and IP issues, but still allow them to test. What else is still ongoing? Documentation. We are rebuilding the documentation. Good example is that the chemistry part is currently spread around the tech manual, the user guide, and the FAQ. And it's useful to have them everything into one documentation so that somebody who's interested in chemistry and not interested into technical details can really look into that manual. On the other hand, the technical manual as such will get enhancements in terms of the workflow of the InChI. So parts that we have experienced now will be found over there, documented, so that somebody who is interested in working with the programming of InChI can get an introduction over there. As well, that will come up the next version, subversions stepwise. Now we have got, I mentioned already, we've got the InChI web demo tool by Frank, which is very useful because you can use that tool to test the current version of InChI, former version of InChI 106, and the latest development version. So for example, if we start the work on inorganics, you can test your inorganics, whether they work or not, and please return your results. That gives everybody the possibility to see how far we came up, and we hope that our development becomes more transparent by that. Frank is going to show the very new version, just built in the last, yesterday. Was a nice train trip, I see. And so there will be more things coming in, especially numbering of atoms, because it is pretty important to have a simple tool to find out how InChI changed the numbering from the original atom to the new one, and do that type of follow-up. On the other hand, Dimitri has agreed to continue with his work, so there will be a GitHub section for him, or there should be one, and so that the InChI, the Windows InChI, has got a future as well. Few remarks about the programming steps, because this is an introduction of some of the parts we have to discuss. Have in mind, we start more or less with an input reader. Then we've got the internal preprocessor, so it's not external, where we do additional structure normalization as needed. Then we've got the canonicalization and connectivity. And then we've got additional layers like stereochemistry and isomers. The canonicalization and connectivity is a critical part. The likelihood that we are not staying consistent with organic chemistry by touching the canonicalization is very high. Yeah, so that's what we try to avoid. So whatever we can do, we would like to do in the preprocessor to adapt the structure in a way that the current canonicalization works with that. And that will identify some of the steps we have discussed in our last meeting over here and why we are going to do them, just to make sure that this way is kept. On the other hand, we have to extend from V2 to V3 mole files. V3 mole files are in already, but we found a few minor issues where things are not properly transported. And we've got a test set for that now to get more into the details of this type of issues. V3 is important for the inorganics and organometallics, because most of those compounds, they've got elements in there that lead to V3 mole files. That is why we need those checks. I just mentioned them already. So the very first things we have started already, and you will just see immediately why, is that we need functionality to break bonds, create bonds, and exchange bonds, especially those bonds that are typical for inorganic compounds. This is the type of structure normalization that is done in this very beginning now, and will lead to this format that is understood by the current canonization. And that's why those steps can already be taken now, because they are the abstract implementation of what we have to work on later on in the inorganics part. Besides that one, just a reminder already from Cambridge, we have to start to think about how are we going to handle versioning. Yeah, so our big hope is there is no change in the InChI or InChI key necessary, because, for example, in the InChI key, we suddenly get major conflicts, meaning crashes, or that in the InChI we find out that some of the forms do not work out anymore. But in the current moment, it looks pretty good. So the assumption is we can continue with 1.x as long as possible. I think that's what most of us want. But the question is, how do we continue? Yeah, so if you call something 1.1, the problem with the InChI key is that you only have an SA, and A only points to any one version. Yeah, so there's no 1.1, 1.2, 1.3 differentiate in the InChI key. But we said if you change the InChI key, we have to change it, the system anyway. Then we come up to something like InChI 2.0. So you see, it's not that easy to handle. Again, if you go down to those types of details, you suddenly find yourself in a completely different position than you started with, because you have to solve those details as well, otherwise you're falling over. Now let's start a little bit about the working groups and where we are with those guys. Reaction InChI has made quite a bit of progress, although it has not been recognized because we wanted to avoid the situation that we had for a long time. So when we published Reaction InChI in 2017, we worked with 104, while 105 was coming out in parallel. So for ages, there was this discrepancy that came up between 106 InChI and 104 InChI, Reaction InChI. Now we are just at the same level. And that's the reason why Reaction InChI is just being released now, and we just have to do the tests. But with the final version of 107. There are, well, actually, time was limited. Most important point over here is that the extension of the reaction format has been adapted, meaning that you can have your starting materials, your products, and your agents in one RxM file. And that is very useful for all people that have to work with that one, because we only have one method to transfer those information into the algorithm. A lot of technical things down the line have been fixed. More interesting is the collaboration with István Öri of ChemExon, because he was the guy who contributed the Mac version. And that was done already using GitHub. So Reaction InChI is the very first version of InChI that was on GitHub. And there you find a Mac version that we may use as a blueprint for the further work of InChI. Perhaps we can talk with István as well. Unfortunately, ChemExon is just merged into Certara. Hopefully, István will stay, and that this type of collaboration will continue. We don't know because of the changes over there. How do we test over here? The US Patent Office database provided by Roger Sale. We normally use the version 2008 to 2011 with 400,000 reactions. And first tests showed that the changes or the discrepancies that show up are based on the changes between 104 and 107. Having in mind that especially between 104 and 105, there were a bunch of bug fixes done that led to other results. Frank already started to implement the Reaction InChI as well into the web demo, so that you can start to play over there. And in parallel, Günter Grete started to develop the idea of a Reaction InChI tutorial. Yeah, so have a very small database, that you can use for searches so that you find an idea what to do with reaction InChIs. Günther decided to leave the group. He is 90 now, which is understandable. But he's still helping with that. And the first point we have to build over here is a search tool for InChIs, because that doesn't exist. Yeah, just a simple search text tool that is searching for InChIs, then therefore for reaction InChIs. And for the next release that we are planning, we're talking about atom mapping. Again, last one is a technical part. Inorganics and organometallics, that's the stuff we discussed 2 months ago. Those are the guidelines that the organometallic group has decided. Everything that is within one cell has to be seen being identical. So you see the different ways of lithium hydroxide, how that can be drawn, but that must be seen to be one compound. Same for the silver complex on the right, and so on. More greener complexes is a long story, of course, but again, we need simple rules to handle them. On this chromium complex, it becomes pretty clear why you need it, because you've got all kinds of combination where water and chlorine is directly bound to chrome, and all of them have got different colors. Yeah, so to distinguish them, we really need this new implementation. You have to keep the metal bonds, unlike before, and distinguish all of those 3 combinations as drawn with the different cells. And of course, we've got our coordinative bond systems, or the best way to call them, where you got this overlaps. You see about the most known one is the one on the lower parts. On the left side, you see the 6 combinations of ferrocene that we are seeing being identical. On the right side, you see historical representations that we stop to use and see them as something else, meaning they get their own InChI. So most important point is now keep connectivity of inorganics and organometallics. It means as well that we have to keep explicitly drawn hydrogens. The exception where you do not have to draw in hydrogen is if you just come up to non-metal atoms, where the valence is counted internally. But you need tools to handle the valences properly. The cheminformatic valence is not faulty. And we developed the workflow for that one. We showed that one already in one of the subcommittee meetings. Those are the conditions we are just following up to see whether we would like to disconnect a metal bond or we would like to keep it. And the conditions are partly labeled on 2 things. First, the type of connection you have, for example, whether it's a terminal metal atom or not. Second, the coordination number. We decided to say, okay, typical coordination, you've got typical coordination numbers that lead to ionic compounds. For example, manganese, if we've got something in the area of 2 and 3, if you take the higher ones, you normally come up to manganetes and other parts that are definitely cannot be disconnected. And the last part of the disconnection goes back to the idea of Pauli, of the electronegativity difference. That's the starting point. It will be adjusted. But he said, you know, if the differences of the 2 elements is less equal 1.7, keep the bond, maybe polarize or not, but in general, for us, it means keep the bond. If higher, break it. And something like this table becomes the base for our programming as well, whether we would like to keep or not those bonds. And this is an example we already presented, sodium chloride. You just go through that one. Is there a terminal metal in the compound? Yes. And you've got the delta En less than Z. So you have to be disconnected, which is standard for sodium chloride. And on the other hand, I mentioned already the bond story. In the prototype, Alex Clark used the any bond to represent especially the organometallic coordinative dative bond types of systems. we prefer to have the any bond staying where it is because it's a query bond and shouldn't be used in a representation of a compound for registration. Instead, the zero order bonds have been introduced, which are those haptic bonds and in the cheminformatics way called coordinative bonds. Because they do not change the H count and therefore do not affect the valence on each of the atoms that are handled. But the problem, the issue over here is, and that will be quite interesting, that those new bond types are not understood by the canonization. Now we have to find a way how to present those compounds in a way that the canonization is able to understand them. And that means we need the bond exchange, and that comes back to what I mentioned before. We need those technical functionality to work on that. That means internally we are just converting them to single bonds, and then just adapt the valence counter, if it does exist, to the related value. So suddenly you may have come up with a carbon with a valence chemical information of 5, so that you keep the right hydrogen count at the end, because the valence as such is not represented anymore in the InChI. That's the trick behind that. Yeah, so we can use valences that are not correct in quotes, but represent the right hydrogen count at the end. And in our current discussion, we orientate ourselves into the output format that is currently used as reconnection layer of the InChI calculation. So it leads to a non-standard InChI. But as seen from our side, that will be the main representation because you keep all the connectivity, and without the connectivity, we are not able to handle the stereochemistry, for example. Yeah, so, and the reconnection is a way to look into that one. On the other hand, we will make sure that the old way is available as well, meaning special parameters. So you've got something like disconnect metal, and we are going to handle there will be a second parameter that is just saying keep as is. So if you, for example, have got a dimer sodium chloride is temperature of 1000 degrees, whatever, that you can build up an InChI, but this, of course, will not be a standard InChI for in that case. Most important for Jonathan, we do not change the InChI of organic compounds. That's our goal. I hope we are going to reach it. Yeah, so where are we now? And that's where we're going to continue tomorrow morning. Salt handling versus metal disconnection. That's what we started to discuss right now. Coming up, oh, actually, that is something Felix, who is on paternity leave, came up with, never looked into that. Do you see any major differences in the representation of sodium chloride and sodium sulfate in InChI? Yeah, both of them look pretty equivalent. Yeah, so it's the same way how they're split up. Of course, sodium sulfate, you've got 2 sodium, the other one only 1, but they're looking really like the same way, except that for sodium sulfate, you got a reconnection layer, and for sodium chloride, not. And that leads to the point that we have a salt handling and a metal handling. Never thought about that because it always looked the same, but it's not. And already that means that we have to integrate the salt handling now into our further discussions. Another point in all of our discussion is about stereochemistry, and the stereochemistry of this octahedron, or whatever is coming up with. We know that we need 3D coordinates for that, or at least 2.5 coordinates, as André described it last year. But how do we recognize the polyhedron? We should discuss. Yeah, how do we know that it's an octahedron? That's the next story. Yeah, but it's something we must have in mind now, because the way we discuss, we always think about this is an octahedron. Yeah, but we may come up to that point, but let's find out. And of course, that leads to the entire story of stereochemistry that will not be solved in the first run. That will be a longer part. Stereochemistry is the other point I wanted to mention. André is working on that one. There will be a bunch of things that we have to work on as well, especially trope isomers that are not handled right now, and the support of the MDL enhanced stereochemistry with and or designators. if the carbohydrates with Haworth and share forms are possible to implement, that is an interesting question, because in the current moment, the mole file does not know the block bond, and something we have to find out. Long allenes are not configured properly, but that's not that much of a thing. But spirocenters is a quite interesting story, because I've got some other issues with other programs in the same issue. Yeah, so we have to check those valid and invalid representations. They may overlap. You see, we're coming up into an area that can become very, very tricky at the end. And that will lead to as soon as we're going to implement it, to quite a bunch of discussions. Yeah, and obviously, Andre is working the Division 8 as well. There are ongoing stories about representation that we have to reflect. Okay, so far, thanks for listening, having a deep dive into the technical parts that are normally not that interesting. But hopefully it was up to a level that was still important for you.